Well, how did you do? I hope you didn't choose C or D. The current has to be running in the wire, and the wire is in the plane of the screen. So the current has to be up or down. It can't possibly come out of the page or into the page. And so which is it? Well, if you're having trouble, you should visualize the rest of the field. What are the circles that these field vectors are part of? And in the perspective drawing, they would look something like this. And so now if you curl the fingers of your right hand and match them up with that circle, you'll find that your thumb has to point down to do so. We've already seen earlier in the course that the sign of the charge carried by charge carriers can't be determined by changes in the amount of charge in places. So I originally introduced this through the parable of the debtors and creditors, where we noticed that the money current, when debtors were crossing the bridge, was in the opposite direction to the direction that the people were moving. Or in other words, we can't tell just by looking at the flow of money whether there are debtors crossing to the right or creditors crossing to the left. Similarly, in current, we can't tell the difference between positive charge moving one way and negative charge moving the other way. It causes the same changes in charge. Likewise, we can't tell the sign of the charge carriers by looking at the magnetic field. Experiment shows that positive charge carriers moving one way produce exactly the same magnetic field as negative charge carriers moving in the opposite direction. In other words, it doesn't actually matter which way the charge carriers are moving. What matters is the direction of the current, which is the same in both cases. I pointed out earlier in the course that we can measure currents by measuring a rate of change of charge, say from one plate of a capacitor to another, but that this isn't a practical way of measuring current. Now we see a practical way, because currents produce magnetic fields, which exert magnetic forces, and so the existence of those magnetic forces tells us that currents are there, and the size of the magnetic forces can give us an indication of the size of the currents. This is how practical ammeters work. Old ammeters used very direct measurements of magnetic forces. Modern ammeters use more indirect methods using something called the Hall effect, which I might make an assignment question about. Note that when we say that currents are sources of magnetic fields, what we really mean is that a current-carrying wire exerts magnetic forces on nearby magnetic objects. After all, the magnetic field is our model for how forces are being exerted at long range. And so, for example, the wire with a current running through it exerts long-range forces on a compass needle, and that is why the compass needle turns to point in the direction of the field as you move it around near the wire. Well, as always, Newton's third law must apply, and so because the wire is exerting magnetic forces on the compass needle must be exerting long-range forces back on the wire. Or, to put it another way, the compass needle produces its own magnetic field, and the wire must feel magnetic forces due to that magnetic field. And so, in general, magnetic fields must exert forces on current-carrying wires. The hardest thing about figuring out the forces that magnetic fields exert on wires is getting the direction right. It involves another right-hand rule, which we'll call the right-hand rule for magnetic forces on wires, or for short, just the right-hand force rule. I'm going to show you the right-hand rule for forces on current-carrying wires first, and then I'll show you a demonstration of it with a real wire. So suppose we have a wire and there's a current running to the left, as shown, and there's a magnetic field in this region which is coming out of the screen. And I must stress, this is not the magnetic field that the wire is producing. This is a magnetic field due to something else that the wire is going to respond to. This field will exert a force on the wire. So, to use the right-hand rule, you first point your whole hand in the direction of the current, as I have done here. Now, you need to be able to curl your fingers in the direction of the magnetic field. So to do so, you have to turn your hand so that your palm faces in the direction of the magnetic field, keeping your fingers pointed in the direction of the current. Now curl your fingers and they point in the direction of the magnetic field, or in this case, out of the screen. Now if you simply raise your thumb points in the direction of the magnetic force that will be exerted on the wire. So let me go over that right-hand rule again. Using your right hand, you point your whole hand in the direction of the current. You then bend your fingers in the direction of the magnetic field. To do so, you'll generally have to reorient your palm, but keep your hand pointing in the direction of the current as you do so. Then you stick your thumb out, and it will indicate the direction of the magnetic force. So try it with this one. We have a current to the left and a B field to the left and down. Try it out with your hand, and what you should have come up with is your hand looking about like this, indicating that the magnetic force must be out of the screen. As we'll see, the forces on current-carrying wires usually aren't very big. But if you use a big current and a strong magnetic field, you can see their effect. So here I've set up some rare earth magnets, and I've set it up so that the direction of the B field between the poles here is that way. And you can see this red wire coming out of the positive terminal of the power source, and so the current is coming out of the screen at you. And so now if you use the right-hand rule, you're going to find that the magnetic force should be up. And indeed, when I turn on the current, you see the wire rise up, and I can push it down and it springs back up. There is nothing sacred about your right hand. We use a right-hand rule because we need some rule. Notice that if you put your hand along the direction of the current and your fingers along the B field, that gives you your magnetic force if you use your right hand, but you could use a left-hand rule where you reverse the order. You put your hand along the direction of the B field and then bend your fingers in the direction of the current, and now your thumb will point in the direction of the magnetic force. We just need some rule, and the one almost everybody uses is the right-hand rule. If you happen not to have a right hand, then by all means use a left-hand rule. The thing that really takes a lot of getting used to with magnetic forces on wires is that the magnetic force does not point in the direction of the magnetic field. It is always, in fact, exactly perpendicular to the direction of the magnetic field. It's also always exactly perpendicular to the current. Well, those two rules then always leave two possibilities for the direction of the force, and you now use the right-hand rule to resolve which one of those two is the correct direction. One more thing is very easy to demonstrate by experiment. Think about this bar magnet next to this current-carrying wire, and the direction of the magnetic field at the location of the wire. If you're not sure why I'm saying that the magnetic field is in the direction that I've indicated in the diagram, remember that the magnetic field around a bar magnet looks like this. And so right beside the bar magnet, which is where the wire is, the field points parallel to the magnet and from north to south. The right-hand rule will allow you to confirm that the magnetic force here would be straight away from the bar magnet. But what about this situation where we rotate the bar magnet so it's now parallel to the wire? Now the magnetic field at the location of the wire is parallel to the current. Well, if you try doing the right-hand rule, you might find yourself a little confused. It seems to indicate any direction at all. And in fact, what you see in experiment is that the magnetic force in this case is 0. What we're seeing here is that there's an angle dependence of the magnetic force magnitude. When the magnetic field runs parallel to the current, the magnetic force is 0. And if we now rotate the magnetic field relative to the current, we find that the magnitude of the resulting force increases until we hit a maximum when the field is exactly perpendicular to the wire.